Does positive acceleration mean increasing speed and negative acceleration decreasing speed? Nope, that's a misconception. What is the opposite of deceleration? Is it acceleration? Wrong. Let's get our misconceptions cleared out. Hi folks, this is the first video in a whole series of videos on 11th standard physics. So we're getting started with motion in one dimension. So let's get started. So the yellow dot represents a particle which is free to move on a straight line. On a straight line, there are only two directions, to the right and to the left. Supposing I want to describe the position of this particle, what do? So what we do is pick a random point and we'll call it x equal to 0. And we're going to take rightward as positive. So we're going to mark off with a meter stick 1 meter, 2 meters, 3 meters, 4 meters, 5, 6, 7 and so forth. And on this side, the negative side, -1, -2, -3, -4, -5. So now we have a coordinate system. And in this coordinate system, with this as the origin, we can now say the particle is located at x equal to 6. Or it may be at x equal to -4. Or it may be at x equal to 29. The point is, you need to specify only one number, positive or negative, to tell me exactly where the particle is located. Therefore, this is motion in one dimension. Supposing the particle were free to move anywhere on this plane, what would we do? What we'd do is we'd set up a coordinate system with an x-axis and a y-axis, and the position of the particle is specified by two numbers, its x and y coordinates. Since I need two numbers, positive or negative, to specify the position of the particle on this surface is considered a two-dimensional space, and this is called motion in two dimensions. Alright, let's get back to one dimension. Suppose that this particle now, which is located at, I'll call it x initial is equal to 6, and let's say at time t initial is equal to 0, at this instant of time the particle is here, and let's say it runs to the left and then back to the right all the way to x equal to 29 or whatever, and finally comes back and stops at x equal to -2. So x final is -2, and let's say this entire motion took 10 seconds. So time is measured in seconds and the position is measured in meters. Now the change in the position is delta x. That is called the displacement of the particle. And displacement or change is always final minus initial, so it's equal to -8 meters. So the minus tells me that the final position is a number that's less than the initial position, which means in this coordinate system, the final position is to the left of the starting position. Doesn't mean that the particle went straight left. Remember, it went left, right, left, all over the place and finally ended up here. All we know from displacement is the change in the position. All we know is during the 10 seconds, the change in the position is -8 meters. One more thing. Supposing I decide to express the displacement with an arrow, that is, an arrow pointing from starting to the ending position, notice that this arrow pointing left represents a negative displacement. We are going to soon see that all arrows pointing to the left come out as negative numbers and all arrows pointing to the right come out as positive numbers. For example, we are going to see soon that an acceleration which is positive means the particle is accelerating to the right, and a negative acceleration means the particle is accelerating to the left. Nothing to do with slowing down or speeding up. Now we define the average velocity during the 10 seconds as the displacement divided by the time interval during which the displacement took place, which is -8 divided by 10. That gives me -0.8 meters per second. This tells me that the average velocity points left. The time interval will always be positive because the time interval is defined as the final time minus the initial time. That is the later time minus the earlier time, which will always be positive. Therefore, the sign of the average velocity will always be the same as the sign of the displacement. Now keep in mind, the average velocity is defined for a time interval. And in this case, the negative average velocity tells me that on average, the velocity pointed to the left. Of course, it moved to the right and to the left in between, but the average velocity points to the left. Supposing now that our particle moves from x equal to minus 5, so x initial is equal to minus 5, at t initial is equal to 0, and let's say it moves at constant velocity of 4 meters per second for 3 seconds. What would happen? 4 meters per second for 3 seconds, that means the displacement in this case is going to be 4 times 3, 12 meters. So from minus 5, it's going to end up at plus 7. The particle is going to end up here. And the displacement in this case, if you want to represent it with an arrow, would be from here to there. But in this particular example, it's moving at a constant velocity. That is, its velocity is 4 meters per second at every instant of time during the 3 seconds. So in this case, the average velocity would be the same as the velocity at every instant of time. In fact, the average velocity is the displacement divided by the time interval, and the displacement, as you can see, is plus 12 divided by 3, that is equal to 4 meters per second. So in this particular example, where the velocity is constant, the average velocity is equal to the velocity itself, but more importantly, you can see that a positive velocity represents a particle moving to the right. Now convince yourself that a negative velocity would represent a particle moving to the left. So positive and negative, in this case, in the case of velocity, tell us the direction of the motion. Let's look at a different example. This is Usain Bolt. Now in this example, I have taken the positive direction to the left. So that's the positive direction. And Usain Bolt runs a 100-meter race. Usually he takes about 9.6 seconds to finish the race. On a bad day, let's say he takes 10 seconds. So let us say the time interval over which Usain Bolt runs 100 meters is 10 seconds. And his displacement, as you can see, is 100 meters. Notice in this example, I have taken leftward as positive, just to indicate to you, you are free to choose the direction, the positive direction, either to the left or to the right, or up and down. If the motion is up and down, that's your choice. Now, Usain Bolt's average velocity over the 10 seconds is the displacement divided by the time interval, that is the V average, and that is equal to 100 divided by 10, that is equal to 10 meters per second. But you don't suppose that he ran at 10 meters per second. That's only the average velocity. Now we know that he starts from rest. He picks up speed. At some point he is moving at 5 meters per second, then 6 meters per second and 7 meters per second. His velocity is changing in magnitude. And when he finally reaches the 100-meter point, he is slowing down, maybe moving only at 8 meters per second. We might expect that roughly, I'm just guessing, that the graph of his speed versus time, I'm going to represent speed in this case with the same symbol as velocity, versus time, it starts from rest. We'd expect it to go up to a maximum value and then slow down to some value like, so this is 0, and I would expect maybe as he crosses the finish line, let's say he's moving at 8 meters per second. Since part of the velocity is much less than 10, he starts with 0, but the average is 10, I would expect at some point in the race, he must have reached velocities more than 10 meters per second. Let's say maybe 13 meters per second. So, let's write down his velocity as a function of time. How do you write that? You put it in brackets. So his velocity at time t equal to 0 is 0 at that instant. And you can see that at the end of 10 seconds, that is velocity at the 10-second point is 8 meters per second. And let's say he reaches a maximum velocity maybe at time t is equal to 7.5. So his velocity at 7.5 seconds is 13 meters per second. What have I listed here? I have listed not average velocities, but instantaneous velocities. His velocity at the instant t equal to 0 is 0. At that instant 7.5, he is flying at a speed of 13 meters per second. So there is a concept of an instantaneous velocity. And at t is equal to 10, he is moving at 8 meters per second. So we have a concept of an instantaneous velocity, the velocity of the object, in this case Mr. Usain Bolt, at an instant. So we need a symbol to represent instantaneous velocity. It's just v, but we want to talk about instantaneous velocity being the instantaneous rate of change of position with respect to time. Why did I say that? Let's take a look at the average velocity. What is the average velocity? Change in the position over change in time. That means the average rate of change of position with respect to time. So let me write that down. The average velocity is the average rate of change of the position. X is the position with respect to time. Now notice, you must not say it's the rate of change of displacement with respect to time. It is the displacement over the time interval divided by. But this is the rate of change of position. The instantaneous velocity is the instantaneous rate of change of position with respect to time. So his velocity at 7.5, at t is equal to 7.5, 13 meters per second is the velocity at that instant, and it is the instantaneous rate of change of position with respect to time. So we need a symbol for this. So the symbol that Leibniz gave us is dx by dt. Now you must not interpret this as dx divided by dt. You must not try to cancel the d's. This is just a symbol meaning the instantaneous rate of change of x with respect to t. Now, Leibniz could very well have invented some other symbol. For example, he could have put a star and put an x and a t, indicating instantaneous rate of change of position with respect to time. Or he could even have used x, t and made a smiley face. But Leibniz didn't do all these things. What Leibniz did is give us this symbol, and by you will see that this symbol is a beautiful choice. It has a lot of advantages. We will learn about that later. For the moment, think of it as just a symbol representing instantaneous velocity. Now at some instant of time, at this instant of time, for example at 7.5, Mr. Bolt is here and is moving at 13 meters per second, and the velocity points in the positive direction, so it's a positive number. A particle moving at a constant velocity would then represent a particle whose instantaneous velocity is 4 meters per second at every instant of time during the 3 seconds. Now we learned this equation corresponding to constant acceleration. We will discuss all this again. V is equal to u plus at. So here I want to take the opportunity to point out that u represents the instantaneous velocity of the particle at time t equal to 0, and v represents the instantaneous velocity of the particle at time t. And this t here is actually t minus 0, standing for the time duration during which the velocity goes from u to v. That is the interpretation of v is equal to u plus at. In order to have no confusion and to always be very clear about what is happening, you must commit to memory 2 sentences. You must always keep these 2 sentences at the back of your mind. The first sentence is, velocity always points in the direction of motion. The other thing you must keep in mind is, acceleration of the particle points in the direction of the net force acting on it. This follows from Newton's law, F is equal to ma. If F is positive, which means it's a force pointing to the right, the acceleration is positive, because if you look at this equation, F is equal to ma, m is always a positive number, there's no negative mass, so F and a are both positive or they're both negative. So acceleration always points in the direction of the force. Let's look at some examples. Let's say the particle is moving to the right. In that case, its velocity is a vector pointing to the right. And let's say its acceleration is positive. What does that mean? Anytime someone says the acceleration is positive, you must immediately think the force is positive. So a particle is moving to the right and a force acts in the rightward direction. So what will happen? It will speed up. So in this example, a positive acceleration represents the particle's speed increasing. Don't be too soon to conclude that positive acceleration means increasing speed. In this particular example, it happens to be true. Let's look at another example. Let's say the particle is moving to the right, so its velocity is positive. Let's say its acceleration is negative. If its acceleration is negative, that means the force acting on it points to the left. It's moving to the right, someone's pushing it to the left. So what happens? It slows down. So in this example, a negative acceleration means slowing down. Let's see what happens when the velocity is negative. So now the particle is moving to the left, so the velocity is negative. And let's say the acceleration is also negative. If the acceleration is negative, that means the force is negative. So particle moving to the left, somebody is pushing it to the left, that means its speed will increase. So here's an example where the acceleration is negative, but the speed is increasing. So negative acceleration does not necessarily mean speed is decreasing. It can represent a situation where the speed is actually increasing. The velocity itself, which is a negative number, let's say it's minus 2 meters per second, and if I push it to the left, it might become minus 4 meters per second. You see, the speed is increased from 2 to 4, but the velocity is decreased from minus 2 to minus 4. Think about it. Okay, let me repeat this last part because that might be a little fast. A particle is moving to the left. Its velocity is minus 2 meters per second. I exert a force on it to the left so that the acceleration is also to the left, which means the acceleration is negative, and the velocity becomes minus 4 meters per second. It's moving faster to the left. But the velocity went from minus 2 to minus 4. So negative acceleration means velocity is decreasing, but the speed might be increasing. Okay, I hope your head is not about to explode. Think about this carefully. What happens to this left moving particle if the acceleration is positive? If the acceleration is positive, that means the force acting on it is to the right. It's moving to the left and someone's pushing it to the right, which means it is slowing down. So in this example, the acceleration is positive, but it's slowing down. So please get rid of this notion that negative acceleration means slowing down and positive acceleration means speeding up. Wrong. Negative and positive refer to direction. And depending on the direction of the velocity, a positive direction might mean speeding up or slowing down. And similarly, for a negative acceleration. Velocity, displacement, force, acceleration, all these quantities have direction. In one dimension, there are only two directions, positive or negative. Positive direction means pointing to the right. Negative direction means pointing to the left. For all these quantities, one more thing. Many students use the words deceleration and retardation. Now, if I ask the student, what is the opposite of deceleration? And what does deceleration mean? First thing, deceleration, student will say, it's slowing down. Fine. Let's agree that deceleration means slowing down. But what is the opposite of deceleration? Should be speeding up. If you ask the student, many students will say acceleration. Because in their minds, acceleration is always associated with speeding up. because they're used to sitting in a car or in a scooter or a motorbike or whatever, where acceleration usually refers to pressing the accelerator, which refers to speeding up. In physics, acceleration can be speeding up, it can be slowing down. So please don't associate speeding up with the word acceleration. So what's the opposite of deceleration? Not acceleration. Because acceleration can be slowing down also. So the opposite of deceleration is speeding up. That's all. There's no other word for it. In the next video, I'll give you many more examples. So, bye for now.